Welcome to a brand new episode of Machine Learning Made Simple. Here we unravel the enchantment behind machine learning, demystifying all the technical jargon. I'm your host, Shogato, and I'm here to chat with you about the revolutionary changes unfolding right before our eyes in the tech world. Let's dive in. Welcome to another episode of Machine Learning Made Simple, where we take you on thrilling journeys into the world of AI. Today we are diving deep into the evolution of the DeepSeek series, a family of open source models that have been redefining what OpenAI can achieve. The DeepSeek models have become the talk of the town, and for good reason. These open source models are being hailed for their reasoning and inferencing capabilities, which are said to rival enterprise grade models like GPT-4o and even the Claude models. And here's the kicker, they have achieved these at a fraction of the cost. Yes, you heard that right. They are like 95% cheaper than those enterprise models, all those API calls. Let's say you make a lot of API calls to OpenAI and you end up paying $10 for all your API calls. Guess how much you'll be paying for DeepSeek? 5% of that. Yes, 50 cents for that many API calls. So that's a 95% reduction in your cost. So severe cost cutting. However, word of warning, these models are built and deployed and released by companies who are based in China. So now if you are hesitant about putting your data out there and specifically to other Chinese companies, and if you're worried about privacy and data leak and all those stuff, exercise caution. So while everyone is busy marveling at the slick question and answer responses, and you will see a lot of videos on LinkedIn where people compare, DeepSeek R1 is the most famous one that people are using. It has reasoning capabilities to rival OpenAI's O1 model. So they open up that and ask a question, hey, what do you think about this? And then it gives a response, and on the side you'll see the O1 response as well. And the O1 response is substantially slower. However, they seem to be almost imperceptibly similar to each other in their responses, and this is fascinating, and most people are thrilled about that. In fact, almost everyone is talking about it. So we're going to take a deeper dive than that. We're actually going to talk about why these models are so efficient and what makes them so cheap to train. And if you really look at these people, and in spite of those chip restrictions that the government has prevented these Chinese companies from having. So China has like this chip embargo where they don't get those advanced chips. So they're kind of GPU poor right now. But in spite of these restrictions, these companies have managed to train these massive models, high quality models with very limited training resources at their disposal. And how did they do that? And can you mimic that if you're a small startup? So this company is a small startup who have really achieved this. And I actually covered an old DeepSeek coder that was released, and it was not very good, and I kind of slammed them as like, yeah, you should just give up. And I'm glad they didn't listen to anyone asking them to quit, because here's where we are. They are rivaling the top enterprise models, and this is great. And DeepSeek R1 is one of the flagship models, and then there is also the V3, whose technical documentation they also released in December of 2024. And their models are quite big, and they're usually hosted on the cloud, but they're fraction of a cost. They cost fraction of what it costs with OpenAI and Anthropic. Now that being said, we cannot cover all the technical details in one episode, so we're going to break it into two separate episodes. In the first episode, we'll see the chronological evolution of these DeepSeek models, and this is a technical episode, so we like to go into a little bit more technical details. Our audience likes that kind of technical details. So if you're really interested in why these models are so superior to the other open source models, yes, some people are saying these models have piggybacked on the Llama 2 and Llama 3 open source models and literally utilized their hundreds and thousands of hours of training hours that are already incorporated into those open source Llama 2 and Llama 3 models. Yes, they have piggybacked a little bit on those models, but they have also trained from scratch, and the amount of optimization that has gone into that is simply mind-numbing. When you really resource constrain a startup, they come up with such great innovations that it will boggle your mind, and that's what we're going to talk about all the shortcuts they have taken, all the optimizations that they have built into just to squeeze that extra bit of performance from small amount of GPU resources that they have is just mind-boggling. So while everyone is busy marveling at and comparing the output, we'll actually look at the models. We'll not worry about the surface level talk. That's easy. But today we're going to break down the nuts and bolts of what these DeepSeek models take. So we are going to start with the original DeepSeek LLM model, which came out in early of January 2024. And here's a spoiler: the secret sauce lies in the training data curation process, a highly optimized, streamlined system that left me amazed as I read through the research papers. The amount of thought, the amount of abstraction and engineering that went into that ingestion process, so streamlined, so optimized, it's just simply nothing short of brilliant. And I always say that a theoretically sound model is worth 1,000 empirical tweaks, or as the great physicist Paul Dirac once put it, physical laws must have mathematical beauty. That's the kind of elegance we are talking about here. In the coming segments, we'll dive into the groundbreaking training methods and innovations that made these models possible. For instance, when we discuss DeepSeek Coder, a true gem of the family, you'll see how they completely transformed the training process to handle massive, complex data sets without breaking the bank. But more on that later. But for now, let's explore how the DeepSeek, the original large language model, set the foundation for this groundbreaking lineage of models, what the optimization that went into it, what the new ideas that went into it, starting with how they completely revolutionized the model training process. And that's what we're going to talk about in the next segment. So the DeepSeek LLM, they talk about, the main paper talks about a lot of things. They base their model on the Llama 270 billion model, but their own 67 billion model that they generate from all those data sets and everything looks like they do it from scratch. Like they do take some inspiration from Llama 2 and all those training processes, but they do a lot of the hard work and the hard lifting themselves. And if you look at the paper, they use a lot of optimization. One of the optimization is like an aggressive deduplication strategy, where they realize that a lot of the data is sometimes duplicated, like especially in coding tasks. The same code, like if you are using boilerplate code, like as an example of a boilerplate code, like if you're building websites, if you're a website designer, like logging in the user, that code is boilerplate. You probably can just copy and paste for every website you build. So that's where the deduplication comes in, because you're feeding in the same data like thousands of times. If you're ingesting those GitHub repos of your own GitHub repos of those websites that you build, let's say you built 1,000 websites and each of them have those authorization protocols and login front ends, and they're just exact copy of each other, then what is the point of like feeding those things into the large language model? Because every time you feed those codes, like if you have 1,000 repositories that you're feeding, you're like repeating the same training process 1,000 times without any achievement or increase in computational accuracy, because you're not gaining anything from it. Like if I already memorize a poem, then memorizing 1,000 times again is not going to improve my performance, right? So that's the whole idea of this deduplication. Deduplication substantially improves memory optimization, and you can tell why. So there are also other things that they implemented which were state of the art then. Now it's kind of common knowledge, like byte pair encoding and all those things. But the main things, what they really focused on, and I want to focus on, is their architecture. What kind of architecture built? So the micro design, they say that they mostly follow the Llama 2 architecture, where they adopted pre-norm architecture. By pre-norm means like usually when you look at transformer architecture, you send your data, let's say the cat is chasing the rat, take the sentence and feed it to the network, and so that it learns that cats usually chase rats. So, and it performs many layers, each layer performs its own thing. There is a feed forward network, and finally after each layer, sometimes you have to perform a layer normalization so that there is no gradient instability, because if some of the layers output spikes, then it can take down the gradient during back propagation with it, so it will totally destroy those gradients and collapse the entire training process. So the layers are usually normalized so that no values get out of hand, so everything is normalized within a certain range. Usually those normalizations are applied after the computation, after the feed forward pass has been performed, and after those data has flown forward through the network and comes out on the other side of the network. But now this pre-normalization technique is that it's like, why don't we perform the normalization a little bit before? And the advantage is that it saves substantially computational resources because you only perform the normalization once. You don't do it after each layer. So that's a substantial improvement in computational optimization. Now, what else do they use? DeepSeek also uses RMS norm instead of layer norm. And we just talked about normalization, and normalization is essentially normalizing so that there is no massive spikes. So output of layer normalization is usually between values of, let's say, -3 +3, because technically, theoretically, it can be -infinity to +infinity, but usually that's not how we see, because it becomes essentially takes your distribution and converts that into a z-score. You calculate the mean and calculate the variance, subtract the mean from your numerical values and divide it with the variance, and you get your z-score. And your z-scores, essentially, it says that how far your data is from the mean in terms of the number of variances. So is it 1 sigma, 2 sigma, 3 sigma, 4 sigma? 4 sigma is like very far away. 1 sigma is around 66%, and 2 sigma is around 95, 3 sigma is 99, and 4 sigma will be 99.9. like 5 sigma is like your data is like really out there. Like, and usually in the 1980s, Japanese went for a 6 sigma, and you see those books, 6 sigma processes. 6 sigma processes is like one out of a million products that you build, there might be one faulty product, because their rationale is that there is absolutely no margin for error. Like nurses cannot say that, whoa, we have a 1% error rate, like, which means when we handle babies, 1% of the babies that we handle do not make it. I mean, that is not acceptable. So they took that idea from healthcare profession that there is absolutely no scope for mistakes, zero error. Like, and how do we get zero error? Like, we go to 6 sigma. When we go to 6 sigma, it's like, it's pretty much, you're out there. Like, it's like the error is almost negligible. So that's where we get the normalization procedure. So layer normalization uses that, tries to convert into a kind of a Gaussian like distribution. However, it's very intensive, like very resource intensive. And the reason it's very resource intensive, you can guess, we're dealing with massive matrices and all those 1,000 batches of data, and you have to take those weight matrices, and then for each you have to calculate the sigma, the variance, and for each you have to calculate the mean. Might be easy to calculate, the variance would be very hard to calculate, because for variance, you guessed it, it's n to the power cube, n to the power 3 time complexity to compute, and it's very computationally expensive to do that. So instead, the RMS norm, what it does, it just normalizes just by finding the root mean squared, which is pretty simple. It keeps it within a range, but it's not theoretically accurate to say, but it keeps the values from becoming too crazy. It does its job. The only result that they're not too large outliers, and RMS norms delivers without exacting the GPU with too much computational resources, and that's all we ask for, and that's what we get. So there are other things that they also implement, and this RMS norm was not implemented in Llama 2. That's one of the key differences between DeepSeek and models and the Llama 2 models. That's where they started diverging. The other thing that they implemented is called group query attention. I'm not going to get into that. It's essentially in any attention mechanism, we have 3 things. We have query matrix and key matrix and a value matrix. And let's say the cat is chasing the rat, and that gets fed into each of them. The cat gets chasing the rat, and like bunch of those sentences get compiled into a weight matrix, and then each of them gets multiplied with q, key, v. So what essentially q and k does, the query and key does, they performs this cross correlation, and by performing those cross correlation, you can see that cat is highly correlated with rat. The cat usually, we don't get sentences like the cat is chasing the dog. That correlation doesn't usually exist. Okay, so the probability is almost 0. When we train with lots of data, that correlation comes up more and more times, that cat and mouse and cat and rat, like not rat, but cat and mouse usually come together. So there's a high correlation there. So Q and K, they get high correlation for those 2 words. And then what it does, it creates a probability distribution. So it spikes at cat, it spikes at the mouse, and that gets multiplied with the value, which is essentially a rotation of the entire sentence. So then those spikes, those probability spikes, picks up those words and then says like, okay, these words are definitely have correlation. Okay, so that's essentially what attention does. But it's, as you can guess, there are 3 matrices to be calculated, is extremely computational expensive. So one way to get around that is to do grouped query attention. Grouped query, what it does is like, instead of doing the entire sentence weight multiplication for each Q, K, and V, they group Q and K. And I don't want to get into the details, but that's what it is. And it improves performance because you're not storing so many matrices in memory, and that really reduces the memory usage by 32 times or more. Okay, so that's a major improvement. There are some design similarities between the DeepSeek models and the Llama 2 models, which they didn't talk about. One of them is the pre-norm structure, where the normalization happens before and not after the feed-forward pass. And another one they also use is called rotary positional embedding. Usually the positional embedding involves any position that gets embedded into a latent structure, but the problem is that there can be infinite positional embeddings because your amount of words can be infinite. So one way is to do is like a rotational thing. So after some time it comes back in a full 360 degrees. So essentially it reduces your parameter space. So it's just simple. And they also use some kind of other activation function called SWI-GLUE, instead of like, usually you probably heard if railway activation, rectified linear unit activation, which essentially is a flat line or slightly tilted line after on the negative direction, and like a linear line on the positive direction. So it cuts off all the negative values, not all the negative values, but there's a slope, because otherwise it like the gradient is causing gradient instability. Actually keeps only the positive value. That's the whole point of the railway activation. The SWI-GLUE is a variation of that. I don't want to get into the technical details, but that's the idea. So that is SWI-GLUE is used both by Llama 2 model and the DeepSeek model. And the reason they keep SWI-GLUE because there are no other activation that can perform better than SWI-GLUE in their use case. Okay, now let's talk about the technologies that are used to train the DeepSeek model, and here the main core ideas come in. So of course they use a very efficient lightweight framework for training and evaluation called HighLLM, HighFlyer, and then they use massive parallelization techniques. They perform data parallelization, they do tensor parallelization, they do sequence and then the most importantly, the one I want to talk about is they're called one forward and one backward pipeline parallelism. So we're going to talk about all that. And the other thing they use is something called flash attention. And if you had trained your own LoRa, low rank adaptation, or PFT models, especially for Comfy or any of your stable diffusion models, then you probably have seen flash attention being used. Actually, we already talked about it in another episode, so we're probably going to skip flash attention for now. The other one we really want to talk about, and that really helps, is the 0-1. It's a partition optimizer, states across GPUs. And then they use a few other things called operator fusion, which we are not going to talk about. Thing that really struck me, that they train in 16-bit precision, okay, but they accumulate the gradients in 32-bit precision. But the whole point and the realization is recent among the machine learning community is that we do not need very high precision. Okay, we just need to be smart about it, because having high precision is not really giving more information. Yes, it's storing more information, but that information is only very little incrementally improvement. Like the difference in functional improvement from 16 precision to 32 precision, maybe 1 or 2%. That's nothing. I mean, we can lose that accuracy, but the performance gain is 2 times. Okay, so what took like 10 seconds with a 32-bit precision inferencing time will now take 5 seconds, but we'll lose accuracy like 2%. I can take that trade-off. And asynchronous checkpointing, this also goes into the 0-1, and they also introduce the same thing where you essentially checkpoint, because if your training crashes for some reason, GPU fault or whatever, memory fault, then you lose all your training. So you have to checkpoint at some irregular intervals, and as the synchronous checkpointing does it in a synchronous fashion, so that while you're saving the checkpoints, you can still keep training. Let's quickly talk about zero memory optimization, which vastly improves the training speed and truly optimizes memory. And this is one of the cutting edge technologies that is being implemented by DeepSeek, and this is not implemented by Llama models still recently. So there are a couple of ways we can implement any kind of parallelization in model training. One is data parallelism. Okay, so in DP, each device, for example, each GPU gets a complete copy of the model and then trains on different subsets of the data. So let's say you have 4 GPUs, each GPU gets the entire model, and assuming that it can fit the entire model in its memory. And we'll come to that if it can fit entire, so then we'll have a hybrid approach. But let's say it's a simple model and each model can fit into the entire memory of each GPU, and then each GPU gets different subsets of the data. So advantage is each GPU works on a complete model and keeps the computation efficient. Now the weakness is it's very memory inefficient because each GPU is keeping an entire copy of the model, and as you can guess, large models cannot be trained in this fashion. The other option is model parallelization. So in MP, the model itself is split across multiple GPUs, and that has to be done for large models. And how do we do that? Let's say we have 4 models, and let's say we have let's say what is divisible by 4. Let's say we have 40-layer network, right? So now each GPU has 10 layers. So the first GPU has like first 10 layers, next GPU has next 10 layers, 11 to 20, the next GPU has 21 to 30, and the last GPU has 31 to 40. All data passes through each of them. Now what is the advantage? It is extremely memory efficient. Each GPU has only part of the model, so nothing is wasted, and now no part of the model is duplicated. But the weakness now is it has lost that granularity, and there's constant talk between the GPUs because GPU 1 has to communicate the data it has produced, because the output of the last layer of the GPU 1 now has to be fed into the input of the first layer of GPU 2, and this process continues across all layers of future GPUs. So this back and forth needs very high speed data transport layers, and that has been recently been obtained by NVIDIA, and it can be done very well by NVIDIA. So even fiber optics would not be fast enough to perform those. However, there are better approaches now that instead of using multiple GPUs and performing those memory intensive transfers, you can have a single die, and there are companies which have those single dies which can completely eliminate this process, and you can load the entire model there. So that's a different topic for different discussion on a different day, maybe in the next part where we discuss in detail the version 3. So insight 1 is the P data parallelization is more scalable than model parallelization because model reduces the computational granularity, but DP, the data parallelization, or it's more scalable. You can just make copies of the model on each multiple GPUs as you keep adding. However, insight 2 is DP is memory inefficient. Insight 3 is not all model states are needed, and this is the crucial insight, right? So not all model states are needed. So when we perform those model trainings, as the data is flowing through, as training data is flowing through, so what happens, there is a forward pass. So KQV weights are calculated each layer. So if you have attention heads, then there is a feed forward network, and there's a little more complexity there, and the whole data flows through the system. At the end, we get an output, and then we match it with expected output and calculate the loss function, and then some kind of optimizer like Adam optimizer forces back the gradient back into the layers in a backward pass called back propagation. So it goes forward and then comes backward, and you can imagine the amount of data which flows go back and forth. And there are a couple of issues here. This will, as you can imagine, there will be definitely bottlenecks that will be created, and one of the bottlenecks that is created is called model pipeline bubble. Not sure if the paper discusses it. The zero DP paper probably doesn't discuss it, but the model bubble happens is like if you have GPU 1 is performing the forward pass, so the first set of data goes in, and then GPU 1 performs the feed forward and then goes to GPU 2 to process, and then GPU 3 and GPU 4. When GPU 2 and GPU 3 are processing the data, GPU 1 is now idle, okay, unless a new set of data set comes in, right? So when you have exhausted your data set and it's going forward, so each subsequent GPUs will start becoming idle. Okay, so at the start of the training phase, GPU 1 is working, GPU 2, 3, 4 is idle, and data is passing across. But after some time, when data is fully processed by GPU 1 and is now being processed by GPU 2 and onwards, then GPU 1 starts becoming idle, then GPU 2 becomes idle, and so on. Okay, so essentially there is a bubble of work that is going on. So this is the pipeline bubble. So there are a couple of ways around it, and I'm glossing over a few details. Like a lot of memory is consumed by these storage of these optimizations, like the gradients, like the Adam optimization has to store the gradients, the velocity, and the optimizer states, and all those things takes about 3 times the model parameter. So if you have even a 1.5 billion model, you need 3 times that times whatever floating point of precision you're using. So 1.5 billion will probably use 10 to 15 gigabytes just to store the optimized states, and 4 times just to store other states, the other gradients, and then you have to store the weights, the KQV values for 1.5 billion parameter model. If we don't do any kind of memory optimization, it can easily take about 44 to 45 gigabytes of GPU RAM without any optimization. That was addressed in this paper called Zero, and there are multiple versions, 0, 1, 2, and 3, and the latest version, they do massive parallelization of almost everything. What they really do, the main idea is you take these optimizer states that you have to save, and initially what people used to do, that they used to offload those optimizer states from the GPU to CPU and then load them back using some kind of synchronization procedure, and sometimes they would just not store any states. Right, so sometimes they will just recompute the states. For example, if you perform a feed forward pass, you can recalculate those because you have the weight still there. So now we talked about the pipeline bubble. Now how to fix this pipeline bubble? So let's introduce something known as one forward and one backward. And in this technique involves having a forward pass with a new micro batch with a backward pass of the previous one. So we know that all GPUs, let's say GPU 1, 2, 3, 4 are storing 40 layers of network. Each GPU is storing 10 layers, and we have to do a forward pass and then a backward pass. Now, in the pipeline bubble, let's say the forward pass is happening and forward pass is moved on from GPU 1, and on GPU 2, 3, and 4, GPU 1 is sitting idle. Now, GPU 1 can start processing the backward pass. Okay, so now it is not idle anymore. So this is how it will work. Step 1, micro batch starts on GPU 1, forward pass, other GPUs are idle. That's fine, we cannot avoid that. Step 2, micro batch moves on to GPU 2, forward pass, GPU 1 begins the backward pass for micro batch 1, right? So now this overlapping keeps the GPU 1 busy while the other GPUs are working. And then step 3 would be micro batch 1 moves to GPU 3 with a forward pass, and micro batch 2 now starts on GPU 1, and GPU 2 can perform the backward pass for micro batch 1. Some orchestration is required to make sure that everything is working correctly in the right order. So this is a brilliant idea, and this appeared in one of the papers written by the NVIDIA research team, and it's a very technical paper to read, and the NVIDIA team usually writes very technical papers, and of course there is a reason they pack as much information as possible, but they're good papers to read if you're interested in actual implementation of these techniques. Now let's talk about the 0-1 partition optimizer states across the data parallelization we talked about. We can perform data parallelization or model parallelization. In fact, we are going to do both. Okay, so that's the main idea we take away from the 0, 1, 2, 3 optimization techniques. To understand what 0, 1 really does, like we'll just focus on 0, 1 because 2 and 3 are just like iterations, improvements on that. Let's talk about optimizer states. What are optimizer states? These are additional data structures that are needed by the optimization algorithms, like the Adam optimizer that is used to train the large language models. For example, it needs to store the gradients, the direction of change needed for the weights. It needs to store momentum, which tracks past gradients for smooth updates. It has to store variance, which helps control the learning rate. So we don't want to get into all that, but you can guess it needs 3 times the amount of parameters. So if you have like 1.5 billion parameters, times it with whatever precision you're using, let's say 16-bit precision, and times it by 3. So it's easily 15 gigabytes of memory that it will be using just for the optimizer states. Now what 0-1 really does is, 0-1 is, by the way, zero redundancy optimizer. It introduces a very clever way to partition these optimizer states across the GPU. Initially, people used to just offload these and recompute as they are needed, and they didn't offload everything, so they have to store these across many GPUs, and half of the GPU was sometimes unusable because it's just storing the optimizer states. So what the 0-1 really did, in traditional data parallelization, every GPU holds a full copy of the model and its optimizer states. In 0-1 optimization, instead of duplicating the optimizer states across all GPUs, the 0-1 partitions them across the GPUs, right? So instead of keeping the same copy of the optimizer states across all GPUs, it stores some in GPU 1, 2, 3, 4. And then if GPU 3 needs optimizer states that are stored in GPU 1, it just has to ask. And so what happens when GPU 2 needs states on GPU 4? So during the forward and backward passes, GPUs only work on their own chunks of optimizer states and gradients. But when it's time to update the weights, GPU 2 might need data stored on GPU 4. In this case, GPU 4 sends the required optimizer states or gradients to GPU 2 over the interconnect, which can be NVLink or InfiniBand. So the memory is saved at the expense of the data transfer. So we need to have very fast transfers, and it was a bottleneck before there because the data transfer rates were not very good. So I'll quickly mention the 0, 1, 2, and 3. So the 0, 1 focuses on partitioning the optimizer states only, that the one we talked about. 0, 2 also adds the gradient partitioning, and 0, 3 extends this to the also partitioning the model parameters. And it's a little bit more tricky, the 0, 3 model optimization states. So we're not going to talk about that. That is pretty much it, but this is huge. This was a huge amount of efficiency that was implemented just by optimizing these training protocols, and this is what gave DeepSeek a substantial edge which they carried forward in their future models. And there's one more thing that we can discuss, which is the dataset curation. They even optimized that, and we can talk about that in the next segment. So let's talk about how the DeepSeek series of models achieve substantial optimization in their dataset curation and the training process. And this builds into the paradigm of DeepSeek Coder, which is a filtered model from the original DeepSeek LLM. Now let's talk about the training optimization and dataset curation optimization, and essentially ingestion pipeline optimization that DeepSeek implemented. And this was specifically observed in the DeepSeek Coder LLM that they released, which is essentially a code generator. And that's where their main idea, the main thought process came in. And this is a brilliant idea. They realized that if I'm let's say a website developer and I build 1,000 websites, some of the codes would be duplicated, like the authorization code, linking authorization, any kind of OAuth protocol that I use. Those codes are boilerplate. We're going to use it over and over again, and it will be duplicated across 1,000 repositories. And if we ingest all the 1,000 repositories and train, then we are training the same data without any increase in accuracy of the model. The model is learning, seeing the same data. It's like, what is the point of learning this? Let's say if you're a musician, what is the point of, if you have already learned a piece, what is the point of learning it 1,000 times? Nothing. Deduplication is the main idea. So deduplication they have performed. Another brilliant insight by this DeepSeek researcher was that there is a dependency parsing problem, because many of the earlier code generators didn't really care about the dependency between different snippets. Like if you have a repository, then the front-end code definitely depends on the model entities that is probably defined in another file. Definitely, if I have, let's say, a Python code where I use a Streamlit to spin up a, let's say, a very simple front end, but it depends on, let's say, SQL Alchemy models, which defines the models, the entities that are going to be ingested, let's say, in a Postgres database. So if we don't train both of them together, if you don't feed both the codes together into the model has no correlation. It doesn't have that holistic understanding that what's going on. So that's why those codes that are generated by those code generators were so disjointed, like sometimes nonsensical. But it doesn't have those contexts that these code bases are split across multiple files and which are interrelated, correlated with each other. So that's why the deep insight was that to perform dependency parsing and create a graph, a node-based architecture where all the things, all the files are interconnected. So if I have a Python import statement or an include statement in C or C++, init file does an imports of the SQL Alchemy model entities, then those two files will be connected by an edge. So and that forms a network, and there will be an entire network of the JIT repository that will be ingested together into the DeepSeek training platform. And that will improve the model's understanding. Okay, all these files are holistically related, and I should train on them together, and then it improves its superior code generation capabilities. It has a holistic understanding. So initially DeepSeek Coder didn't perform well because it was memory limited, but now those training processes, those training optimization, those ingestion processes have now been transferred to V3, which we'll talk about in the part 2, and also reasoning, the R1 model, and that has led to its superior reasoning and code generation capabilities in the recent iterations. So this is a huge quantum leap in optimization techniques, because people do data curation, but people haven't thought about that we need to do all those things. We need to perform deduplication. That's insight 1, that people didn't think that we need to perform those abstract level dependency linking. That's insight number 2. These two provided a substantially step up from previous learning of the large language models on the coding repositories, and that totally changed the game. And that was the main difference of architecture of the DeepSeek coder from the other code generating platform. Of course, OpenAI have also implemented a variation of this, because this was published open source. And then there was a later paper when the version V2, which we will discuss in the part 2, where they also implemented a new technique which is multi-headed latent attention, which we'll discuss in the part 2. Is quite straightforward. It's just a latent representation of the key values. But for now, let's focus on what is the major insight that they have implemented. 3 major insights. One is improve pipeline optimization. How do we do improve pipeline optimization? Parallelize everything, using 0, 1 to parallelize everything. Use one forward, one backward pass to utilize every and squeeze out every GPU that is being used. Like, squeeze the extreme performance from every GPU resource that is available, and then reduce the memory overhead, reduce the training overhead by whittling down to bare minimum amount of quality data that we can use. So essentially what they focused on is improving the quality of the data set that is being ingested rather than by the quantity. Instead of throwing large volumes of quantity of data, they focused on improving substantially the quality of data, because if we have few amounts of quality data, that our training time is much less, but our performance, our knowledge of our large language model that is trained on these will be substantially better. So that's pretty much it, and we have discussed so many technical topics, and that's where we're going to stop today. And we're going to continue with the version 3 and the R1 models in the part 2 of this series, and we're going to talk about that in the next episode. So thanks for listening, and talk to you next week. That's a wrap for today's episode of Machine Learning Made Simple. If you have questions or want to explore AI topics further, please don't hesitate to leave a comment. Until next time, keep exploring and enjoy your AI adventure.